And this is technically the final example, but I do want to show you one other thing after this, so don't get too excited. We're going to say that from a 210-foot cliff, David observes a lighthouse that is 430 feet offshore. We want to find the angle of depression from the top of the cliff to the base of the lighthouse. Okay? So we're looking for the angle. We're not given the angle, we're looking for it. And I don't know why we care, but we do. All right, so here's the cliff. All right, how tall is the cliff? 210 feet? Okay, so I'll label that. This is 210 feet. All right, here's David. He lives dangerously, so he's going to sit out here. He's just sitting here. There's something wrong with his head, but anyway. Okay, so there's David. He's just sitting on the edge of the cliff, okay? And he is looking down at a lighthouse. The base of a lighthouse. So there's a lighthouse over here, which I can't draw, but anyway. What goes on top of a lighthouse?
A little house looking.
Shouldn't it be taller?
A light.
I don't know. Anyway, there's a light. I don't know. There's a lighthouse. It's like a candle. It's a giant candle, okay? There it is. Right. David's looking there. Where is the triangle in this situation?
It's going back.
It goes back this way, right? Okay, so it's this way. Okay. How far is it from the lighthouse to the base?
430.
430? Oh, man. Try that again. 430 feet. What am I looking for?
The angle.
The angle of depression. Where is the angle of depression? Is it
Base.
inside the triangle or is it outside the triangle?
Inside.
Okay. Remember that the angle of depression is from the line of
Sight to like down.
yeah, so horizontal to the line of sight. This technically is the angle of depression. This is where people go wrong. This is what you were talking about. This is the angle of depression. Where do you think people put it?
Inside.
They put it right here. Here's the thing. This angle right here, never used. Never, never, never use that angle, ever. This angle is exactly the same as this angle. You put your angle of depression in the same spot you put your angle of elevation. Okay, you don't ever, in fact, it's like a trick question. You don't use an angle of depression. Because of the whole like parallel lines cut by a transversal and alternate interior and exterior angles are congruent, this angle of depression is exactly the same as this angle of elevation. So you always put your angle there. Never put your angle up here, and don't even bother to try to draw an angle of depression. Just relocate it into the triangle, and it will always be the one at the bottom looking up, whether it's elevation or depression. You will never use this one, okay? And that's the one we're looking for. That's a much better lighthouse than mine. I should have let you draw it. Okay, so is this sine, cosine, or tangent? Tangent. And guys, about, I don't know, I would say almost 90% of the time, angles of elevation and depression are tangent problems. It is rare that we are interested in the diagonal here. The only time I can think of that we're really interested in that, do you know those guy wires that go onto light poles? Do you know what I'm talking about?
Yeah.
The guy wires? We might be interested then because we might need to know how long that guy wire needs to be, that diagonal wire that stakes it to the ground. Most of the time we're not interested in the diagonal distance, so a lot of times the hypotenuse doesn't matter, and that will make it a tangent equation. So we know that tangent of theta is equal to opposite over adjacent. How do I solve that? How do you always find an angle? You second it. So you second tangent, so inverse tangent of 210 over 430. And that is going to give us our angle of not only depression, but of elevation, because they are always the same. So, what is it?
26.
Okay, so it's 26.02959219 degrees. And I have two significant digits only, so I have to round that to here. So 26 even? Okay, that's the angle of depression and the angle of elevation. Do you guys understand that? Are we ever going to put our angle right here?
No.
No, never. Got it? Okay. Well, Well, for your final thing for this section, I'm going to draw a triangle, and I want you to solve that triangle for x. Here's a right triangle. Let's say this is x, this is 21 degrees, and this is 53 feet. So we're going to pause right here, and I want everyone to attempt to solve that for x, and let's see if everyone can get it. Okay, so what did you guys tell me you got? You got 130.
I got 140. 138.
So the reason I pointed this out is there's not an example in this section when the variable lands on the denominator. So I wanted to show you that. If we write a tangent equation for this, we get tangent of 21 degrees is equal to opposite over adjacent. So 53 over x. So if I stack this over 1 and I cross multiply, I actually get x tangent of 21 is equal to 53. Then I have to divide both sides by tangent. So x equals 53 over the tangent of 21 degrees. And that gives you approximately
38.06.
138.
It's 266.
I haven't finished yet. 0.0 what?
0697204.
Okay, and that's feet. But because it's only two significant digits, I need to round to this guy right here. So that actually bumps it up to 140. Okay, and David pointed out something that I liked a lot. He said it's easier if you actually find this angle, which turns out to be 69, okay? And then you use it to write a tangent. To write a tangent equation instead. And so that can keep you from having, that problem where your variable's in the bottom. So I could solve this as the tangent of 69 would equal opposite over adjacent, so x over 53. And it kind of saves you a step. But it really doesn't matter. You should be fairly comfortable either way. So just figure out what works best for you and just always do it that way. And we end up getting the same thing. Right? Uh-oh. Okay, so that wraps up section 2.4.